Long gas law example. Here we have a much longer problem that involves not just a mixture of gases, but a mixture of gases that actually react with each other. So we have two bulbs that are connected by a valve. The larger bulb has nitrogen monoxide at 0.6 atmospheres, while the smaller one has oxygen at a partial pressure of 2.5 atmospheres. And we want to determine what gases remain after the reaction goes to completion and their partial pressures. One piece of information that'll be very useful is to know that at both the beginning and the end, the temperature was 22 degrees Celsius. To do this problem, we have to do many steps. We need to know how the gases react. To do that, we need to have moles. We can't simply combine these in terms of their volume and pressures. Once we convert to moles, we then have a limiting reagent problem, where we do this exactly like we did in previous classes. We see which of the reactants is the limiting reagent, use that to determine how much of the product is made, and how much of the excess reagent is left over. At that point, we'll have the moles of all of the species, and we can convert back using the ideal gas law. So let's start now by converting everything to moles. For each gas, we have the liters, and the pressure, and the temperature. And so we can use PV equals nRT to solve for moles. We will need to do this for both the nitrogen monoxide and the oxygen. We will want to do this before the valve is opened and before the reaction happens, so we can use the volume given for each. For nitrogen monoxide, we have 6 liters, 0.6 atmospheres, and we know our temperature. Once we fill into the equation, it's simply a matter of typing into our calculator to get our answer. Because we're going to be doing a lot of calculations here, we want to make sure to hold a few extra sig figs as well. From here, we'll do the same thing for oxygen. With a 1.5 liter bulb, 2.5 atm, and still 22 degrees. And now we have our moles of each reactant. From here, we have a limiting reactant problem, just as we did long before we knew what ideal gases were. So for finding the limiting reagent, well, we could go through and do the much longer version while we take each of our reactants and we solve for our product. In this case, it may be better to do this a bit simply. We can look at our oxygen, and we can say that for every 1 oxygen, we need 2 NOs, which means that if we have 0.15 approximately oxygens, we are going to need double that many moles of NO, so about 0.3, and we definitely don't have that. And so because of that, NO is going to be our limiting reagent, and that's able to get us to the answer the quickest. So from here, we'll need to go through and decide what happens after the reaction occurs. We initially started with this many moles of NO and this many moles of O2. We know that this is our limiting reagent, and every bit of it will be converted into NO2. If we do this mole ratio, we can see that all of it is converted into NO2. So now we have two numbers. We know that our NO is going to equal 0 atm because it's our limiting reagent. And we also know that our NO2 is going to be 0.148 moles. So our last thing to solve for is oxygen. So what we need to do here is start with our starting oxygen, subtract how much we used up to get our final. We started with our 0.1548 moles. We used up however much was used up by using up all of our limiting reagent. So we have a conversion in here that we need to do. We start with our moles of our limiting reagent, we use our mole ratio, and now we know how much was used up. We can do that all in one step pretty easily to get our answer. Now that we have our moles of everything, we can go ahead and convert all of these back into pressure by using PV equals nRT. And for each of these, fill into the ideal gas law. Be careful when we fill in our final volume to make sure that you're encompassing both bulbs, because now the gas is allowed to fill the entire container. For oxygen, for NO, because it was our limiting reagent, we're able to just say that we have 0 ATM, because 0 moles equals 0 pressure. We again have to make sure that we fill in the volume of our entire system, both bulbs. And now we have our partial pressures of all of our gases. The last thing we need to do is find our total pressure. So of course, to do this, we simply add up both of our other pressures. And then we're all done with our problem.